approach it from different way. Rather than writing the Hooke's law, writing the normal force summations, we're going to use an energy method for the structural analysis. Okay, why don't we use the Hooke's law throughout the whole course? The reason is very clear. Because in reality, a rod is a continuum. Okay? Even though it can be idealized as a spring, that can be described with a spring constant. Okay? But there are situations where these cannot be fully captured if you have a rod subjected to distributed load. Okay? So for a spring, it's an element that supports the end loading. Okay? So you can have spring stretch. So the way you apply force is apply the force at the end of the spring. Okay? You don't consider the force along the length of the spring. Okay? So of course, with the event of parallelism, a continuum, okay, can be cut into many elements. So each element can be modeled as a spring. Okay. So you could have one spring, two spring, and three spring. So you have one element, 1, 2, 3, 4. Okay. If this whole length is L, you could divide it into a quarter. So the stiffness here becoming EA over quarter length. Okay. So this individual spring constant will become 4 times EA over L, which is 4 times the original EA over L. Okay. This can be done by a meshing. Okay. However, the question remains. Okay. In the model, we previously only considered tip loading, the loading at the end. So of course, when you break up, okay, under tip loading, so this force will be the same. The force acting at the bottom is equal to the force acting at the top of the same spring, and then this one is going to continue. So means your 4 spring element, each of them is subjected to the same force. Okay? Same axial force. But the question comes, what happens if you have the distributed loaded? If the force now is on the surface, okay? So this force accumulation, okay, even though the profile is constant, but it keeps accumulating. Okay? So when you cut here, you only see this amount of the force. But if you cut here, you see the double amount of the force. Okay, if you cut here, okay, this could be Q L over 4, this could be Q L over 2, and then here you have a Q 3L over 4, and at the very top you have the extra distributed load. Here we define Q as the total force divided by the length. This is in the case of uniform distributed loading. But there might be cases also. The loading could be depot, okay? Rather than this uniform loading, could possibly have this loading, okay? Why do you have this kind of loading? Okay, in the aircraft, or in the case of working wing, okay, this could be the wing of the bird, So this will be subjected to the greatest tangential speed given the same stroke speed. So this is the radius times the angular speed squared. If that's the case, then your normal forces or your loading is going to be non-linear. Okay? So this is the reality. So in this case, you can model a rock as a simple spring which support the normal forces. But then, in the solution, this is the nature. We can't change it. How can we change the physical nature of distributed loading into N loading? So this is what we're going to do. Okay? And we can start off with some very simple case. So before we start with any theory, just have a quick check, okay, of the concept. Okay, here I have a rock dimensions, but this time around I only divide it into half. Okay? If the force is acting, okay, with the tension per unit length, Q is equal to force of F. And then, if I consider one of these, how do you turn the surface force into the tip loading? So if I say this is the external surface force, and then this one I convert it into a normal force. Let's say this is the F1 and this is F2. Okay? So how would you make a quick judgment?学有些人之前，一定要会懂得叫做这个叫直接做一个内插也好，或者是分配。Okay, in this case, how much is the total force? If this is the half of the length, this external force is half of the length times the density. This is your half of the length times the total force over the full length. This is F of that. Okay? Can you tell me how do you turn this surface force into another force?有所谓什么高深的理论，这东西摆在这里，来小小的东西，你看看。说一个模嘛，跟一个模。没有我现在都是平均的 surface force， I'm talking about surface force. Okay, I already calculated how much the total external force acting on the surface. This is F/2. This is on the surface. How do I divide the force to the two nodes? Okay. free part. Yeah, correct. So this total force on the surface, okay, is going to be divided by half. Okay? So in the end, you will have quarter force on the not 2, quarter force on the not 1. Okay? And then next question. What happens if the force distribution is linear? Okay? If this is the maximum force at the top and the bottom is 0 along the full length, how much is the total force applied on the surface? 来，欧洲同学你厉害吗？
把它分起来。
几分起来对吧？不用积分的。
这个完全是2跟它的长度的24道有关。
Yeah, what's that? The total, sorry? Yeah, the real? The total.
No, total.
Yeah, if this is a magnitude, and
0.
this is f per length, okay?
0.5.
Yeah. Yeah. Right, this is half. Okay? 所以你学到这里，你可以给你学的微积分一个总结。So what's the summary of your calculus learn? This is something very close to your calculus. Okay? So what's the geometry that is most important in your calculus? Do you know? 所以你大一学的微积分学了这么多，你就拿两个几何来，或者是元素来解释。So what's the essence of your calculus? It's also valid to fundamental. From this geometry, what you learn? You learn about interpolation. And what's the geometry that stands good for interpolation? Is f. If you are doing the integration to find the total force, you are integrating this. Okay, the two geometry that you learn. First is triangular area. Second, if it's not starting with 0, both sides are not 0, then you have the trapezoidal area. Okay? Geometrically, you should have this idea. And then next, you might have learned about gradient. Okay, but in this case, the force will be cancelled. And then the question next. If this is a distributed loading, okay, I take this simple one. The one starts with 0. 0 force density. Okay? This is 0. I know this total force is even lesser. This is half over L. This total force is F over 4. And then my question here. And have you make your mind how much is the nodal force? Are you going to make it 0 at the tip? Are you going to make it alter the total force? So what is the right choice? Okay, 所以到这个时候你会有一个抉择，你就是拿等比的方式去分布力嘛，没有。So are you going to assign the nodal force in proportionality? No, not necessary. So there are a better way. What's the better way? You're going to do it by energy method. Okay? So, yeah. So what's the simplest energy method that you can use? Again, I wouldn't start something complex. I would start with the one that is simple. Okay? If you have the spring, okay, you subject it to end loading, let's say big F. Okay? So if you're able to use energy method to solve this spring extension, it is possible that you can use the same method to do the division of the distributed loading. Okay? So we only start with the tip loaded spring. Okay? What's the energy method for the tip loaded spring? You know that this increase in the force, okay, is in-proportional to the tip displacement. So how much the energy? Okay, you define the work done, or you define the elastic energy storage. It is integration of the spring force with respect to the U. And how much is this spring force? In this case, the spring force is Ku. So by doing the integration of Ku du, starting from U to 0 to U to the final, then you have the half Ku squared. Okay? So here, even though I am doing the work, but because this is now taking account of the elastic force, then I write this as a U, big U. This is the strain energy storage. Okay? In that way, how do I find the force? Okay? Okay? How do I find the force from this? It's very simple. You have the energy. To find the force, you use the Castigliano theorem. How Castigliano theorem is? You are doing a partial differentiation of the strain energy with respect to the tip displacement. Okay? You see this expression? If you differentiate half Ku squared, in the end you have half K times 2U. So in the end you have Ku, and this Ku is your tip loading. So this is what you call Castigliano theorem. Okay? And yeah, this Castigliano theorem for a spring or hook saw is nothing new. But now let's analyze this again. Okay, in the case of the spring, you have two tips, two nodes, one moving with U1 and the other end move with U2. How much is the strain energy? You can write strain energy for this is half K times the extension. How much is the extension? It's U2 minus U1 squared.
It's not U square minus U square.
No, spring extension. You're talking about the extension of the spring. Okay, I don't have the spring with me, but if you imagine the spring there, okay, let me show you.
Don't worry.
Okay. And you have the spring here? So in this case, I will start with the spring that is fixed at the top. So if you let go, you only focus on the bottom displacement. If the top is fixed, so you have the extension being the bottom displacement minus 0. Okay. However, if now I'm not moving the bottom part, but I'm exciting the base at the top, okay, then how do you find the extension of the spring? It must be the bottom displacement minus the top displacement. Otherwise, I cannot precisely know the extension. What is hook saw? Hook saw is about the spring extensions and the force. But it just happened that you always fix the spring at the top, then you say, oh, I just care about the bottom displacement. But in reality, what you really care is the extension, the length change. What is the final length and what is the starting length and what's the difference? And that difference times the spring constant will give you the spring force. So you see that when you have the base excitation, the spring can have both end moving. So if not clear to you, then look at this one. This one will be clearer. I will have a big marker of two sponge. Okay? So how to define the spring extension of the lower half? Okay? So now the top sponge and the bottom sponge move differently. Okay? At one excitation. So how much is the extension? And then next you see, when I excite them into higher mode, the bottom sponge and the middle sponge will move opposite to one another. How do you calculate the spring constant? How do you calculate the spring force? You really need to know the extension, or so-called the length between the two separation. Okay? Okay, now let's try to find out what's the usefulness of Castellano theorem. Okay. Okay, it's a big name, but the operation is very simple. If you have the strength energy being differentiated by the displacement, okay? Okay. Then you have the force equal to differentiation of the strength energy with respect to the displacement. In this case, if you differentiate with U1, you're going to get F1. If you differentiate it with respect to U2, then you're going to get force F2. Okay? So this is like, it might look like a free spring, but when it's being cut of the spring, okay, they are not free. They are restrained by your neighbor. Okay, you know how to move across a crowd. Okay, you have to really push someone in front of you. Yeah, if someone behind you pulling you, then you also feel the force. Okay, so these are the force between your neighbor. Okay, so let's see. By taking the same strain energy for the same spring, but because the top node and the bottom node will feel differently. So how this differentiation get? If you do the differentiation with respect to U1, then you have the half K U2 minus U1 times 2 times, you know how to do partial differentiations. After doing these as a function, that is 2u2 minus u1, you still have to differentiate something inside. Del u2 minus u1 divided by del u1. Because not u2 is an independent variable from the u1. So the first term is going to be 0, and then the second term is going to be minus 1. As a result of these partial differentiations, so you obtain the fourth one is equal to k u2 minus u1 and minus 1. So you have k u1 minus u2. Okay? So likewise, let's do the partial differentiations of the at the node 2. Okay, this is the same expression. If I now differentiate it with u2, then I have half k 2u2 minus u1 times del u2 minus u1 divided by del u2. In this case, partial differentiation of the u2 is going to be 1. Partial differentiation of the u1 with respect to u2 is equal to 0. So in the end, your expression is k times u2 minus u1. Okay? Because we can write these two forms. Okay, what's the two forms that you're going to write? Force 1 and force 2. You write them in the vector form. You're going to express them as a matrix times a displacement vector u1, u2. So let's say f1. F1 is the first row to go. So this is going to be k u1 minus k u2. And then next, how about this force 2? That is minus k u2. No, this positive k u2 and minus u1. So in this way, you obtain the same thrust element as we did. But this time around, you don't really have to care about direction of the force. Okay, like we did. This time around, so long as you write it correctly, your partial differentiation will take care of the sign convention. So that's a good thing about energy method. Your partial differentiation will do it. But remember, when you do partial differentiation, u2 and u1 are independent variables. When you do partial differentiation, one of them will become 0. Okay? Okay, do you get it? Okay. Then next, I will jump straight to the loading. Okay, there are many operations here, but I will go to the very last slide to tell you what is the thing we like to solve. In the case of uniform loading, how will you find the normal force? Okay, so in finite element there might be some interpolation function. Okay, expression quite complex, but why not we go something simple and straight to the point, straight to the core of the method. spring is equivalent to a rod. Okay, this is a spring. This is rod. Okay. But for individual rod, okay, this is full length. This is a small length. So if you now subject it to distributed loading, okay, let's say Q. Okay. Q has a unit of Newton per meter. Then how much the force acting on this area? The force is equal to Q times dx. Okay. And how much is work done? So previously you learned about this is the tip displacement, and you also learned about the energy storage here is U2 minus U1 squared times K divided by 2. So for this thing, then by getting this rod here, if the displacement is distributed, okay, you could possibly have also U2, okay, but let's say this is the starting one, U. The next point will be U plus du dx times x. Okay, so this is the kind of the interpolation or extrapolation. So the displacement is going to change. So in that case, we will be able to find how much is the energy stored. Okay? So the expression is going to be more complex. Okay? So am I going to write this is your displacement difference? Okay, this is a displacement difference. This is going to be U plus du dx minus u and then square and then times what? Your k here is EA over dx divided by 2. Okay? So this expression is going to be quite a complicated one. So even I can do that. Okay? Then I have du dx square and EA dx. So this expression, this small amount of the strand energy is going to be du dx square divided by 2, and then what else? It is EA dx. Okay? And this is solely coming from the energy point of view. Of course, if you know what is the meaning of du dx, okay? If you cannot see the chain of displacement from u U2. Okay, this is difficult to see. Then why not I draw them in this way? U1 here, after some distance, this is U2. This distance is called dx. You now know the meaning. Okay, let's come back to the Hooke's law. In the Hooke's law, you learn about force versus length chain. But you also learn that if this is the rod, okay, and if this is the force, I can rewrite this as force over the area displacement divided by the length. Then I'm going to get the Young motion. F is equal to Kx, Ku. But remember, Ku is EA over Lu. So you can rewrite this as force over the area, which is the stress, is equal to the U over the starting length, that's the strain. Okay? So in that way, this expression of energy looks something that you are very familiar with. This is your half the strain times the stress times the cross-sectional area times the length. So 你的应变是什么？基本上是应变乘上应力，然后对面积对长度积分。Okay, if you now do this integration, okay, integrating from x equal to 0 to x equal to L. Okay, in the case here, because this is the uniform loading, you are going to have uniform strain. Okay? Yeah. Is it going to be uniform? We got to take a look. Okay? So, yeah, it is uniform. Then you can simply write the expressions. Okay? But now what happens is if the strain is the strain going to be uniform? Let's look at the spring. Tell me, under the constant weight, okay, let's come to the end now. Not this one. Let's come to this. Okay, this one. So let's see this example. This spring is subjected to a constant gravity. Okay? So for each segment, they are subjected to the same weight per unit length. Is it going to give you a constant extension? Apparently, let's see. If the pitch of the spring represents the starting length, okay? If I count the pitch, I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first 10 pitch of the spring is only this length. But let's count the next pitch, next 10 pitch. 1, 2, 3. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this second 10 pitch, the elongation is much larger. Okay, and then let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even longer. Okay? So why is that difference in the extension when you are subjected to uniform loading? Okay? From the gravity. Okay? So this has to do with accumulated force coming from your neighbor. Okay, when you cut it here, you see 10 pitch wave. When you cut it next, you see 20 pitch wave. You cut it on the top, then you see 30 pitch wave. So even though the loading on the surface is uniform, but they are accumulating. Okay? So in that way, okay, do you see that? It becomes complicated to do the calculation. Okay? So rather than jumping, okay, I try to jump, but apparently the calculation is not that straightforward. So that's why we'll come back one step back. Okay? Okay. We got to do some basic thing about interpolation. This is what we did about Castigliano theorem. We also do the differentiation of the strain energy of a spring with respect to knot 1 on the left and knot 2 on the right. In the end, we get the same element. Okay? So we apply this already. And then next, we go one step further. Rather than writing them as a Castigliano theorem, okay? I can re-express the Castigliano theorem in the other way around. I can write them as total energy. Total energy is the difference between strain energy and the external work done. I think too many, so you may not see why is the subtraction not 0. Okay, let's take the example of the spring again. How do you tell from the example here? Is strain energy equal to the work done? Take this example. 所以你这弹簧储存的势能，是不是等于它重量做的功 ？Okay, here's the question: Is the work done by the weight of the spring equal to the strain energy stored? Okay, if you are not sure, then let's draw the question. This is the force versus the displacement. The strain energy storage is this amount. But what is the work done by the weight? The weight will change. So the work done by the weight is so what the total energy method is telling you is the total energy is going to be equal to the strain energy, the one in the red, minus the work done. This is the force F, force P, they must multiply with the tip displacement. OK? 所以从这个式子你看到没有？它回归是零。OK? So why the difference between work done by the weight is not equal to the spring energy? Can you tell from this example? So why this are not 0? Yeah, can you try to explain? Okay. How about the guy? How it is? 系统的总能量是 的应变能减掉你的重力做功。从这例子，它要等于它是等于。So it's the difference of strain energy and the work done by the weight 0 or not 0. Is it 0 or not? What is 做功等不等于你的这个应变？Okay. So just show that. Is it equal or not? In this video, is the work done equal to the strain energy? Equal. Not equal. Okay. Why is not equal? Work done in this case is more than the strain energy stored. So you see the spring vibrating. Then they got the overshoot. Okay. So let's see again. When the weight pull the thing down, the work done by the weight is more, so it's exceeding the equilibrium position. So eventually, you settle to this balanced position. Only at the balanced positions, then the difference between the two is 0. So in this case, you do the partial differentiations of the total energy with respect to this variable. Let's say U1. Okay? Then if this is U1, okay, then you have P del U1 del U1. Okay? So this is going to be 0 when they come to equilibrium. Okay? In this case, so you're going to do this difference. So from this expression, then you find what is your P. What's your applied force? The applied force is equal to these expressions. Is back to del UE del U1. OK？ 所以这些公式有一个重点，就是你要公式越来越复杂。公式成立的条件是什么 ？As the formula get more complex, how would I judge this formula is right? It's like your software, backward compatibility. Okay? In this case, this is the minimum energy method. But after some operation, it reduced to your Castigliano theorem. So this minimum energy theorem must be valid to some extent. But if you just reduce the Castigliano theorem, what force should I care about that? Okay? Next, then we come to the reason why we need to make the thing so complex. Okay, the whole reason here is, why should I write minimum energy theorem? If it can reduce Castigliano theorem, why do I do this extra step? Okay? The whole reason here is your minimum energy theorem do not just account for the tip load. Okay? So here let's see. If you have two nodes, U1, let's say on the top, and U2 at the bottom. And if the bottom force is F1 and the top force is, bottom force is F2, top force is F1, then you must have the work done by external force F1 times U1 by external force F2 times U2. 所以看到没有？你在写这个那个系统的总能量的时候，应变能你已经会算了。那做功你会不会算？做功是什么？外力做的功，如果是正的方向 ，OK， 我们看这个力跟力是正的方向，那就是正功。但是我们这个式子是减掉正的，所以 this is a positive word. This is minus positive work done by normal force. Okay? Normal force. This is the sign. Okay? If you do like that, you still reduce your Castigliano theorem the same. Let me rewrite this. Okay? Anyway, you can do differentiation of total energies with respect to U1. Then you have del UE, del U1 minus F1, del U1 1 minus F2 del U2 del U1, and this is 0. So in the first expression, you got your F1 equal to del UE del U1. If we now do partial differentiation of the total energy with respect to U2, we can repeat the same, del UE del U2 minus F1 times 0 minus F2 times U2 del U2 equal to 1. So in that way, Castigliano theorem still remains valid if you are re-expressing it using the total energy. Okay? But that's not the whole about the total energy. The whole thing here is important because this provides you another way of defining the work done by the surface traction. This Q force has a unit of Newton per meter. Sometimes you call it a surface force, sometimes you call it a traction. Okay? So if you are not sure what is traction, you heard about tractor. Okay? Traction is the force of tractor. 所以你们一般表面张力，你除了讲这个 surface force，OK， 你也可以把它叫成是 traction。traction 的源头就叫拖拉车 tractor 的力。Okay, in this case, if I now have the surface force Q, now I can extend my Castigliano theorem one step further. How do I explain it? I can minus the work done by surface force, but this surface force has to do with small incremental displacement, du. So then I have to integrate q du. Okay? So that's the point that we come back. Okay. How do you find this q du? Okay, we need to do some interpolation. So we have already carried about this rod have displacement u1 and u2 on knot 2 and knot 1. Okay? And if you try to draw displacement chain versus the length x, this value is x equal to L, this value is x equal to 0. This displacement chain is starting from u1 and end with u2. So in a way, how do you write the expression for displacement function? Okay? So if you cannot see this, then why not we do the rotation u and x. This is my u1, this is my u2, and this is my length chain from 0 to x equal to L. Okay, what do you tell me the equation for this line?
Is u2 minus u1 over 0, no, L minus 0 by x plus u1.
Yes. So this is your variable of displacement. Okay. 我看国中数学那有学过。Okay. So this is not very difficult. This is just linear interpolation. You should learn it in the secondary school math. Okay. Finite element starts from here. You should know the interpolation. And then next, do you see it here? If I'm going to express this expression, okay, I'm going to do the integration. But here, my ultimate purpose is not to do the integration. My ultimate purpose is to, if this is q constant, okay, then I should have this integration of the displacement. Okay? But now, what's next? If I'm going to find the force contributed by this surface force, I should do del pi del u1 equal to, okay, the rest is the same, ue del u1 minus f1, and then for this part, after I do the differentiations, I should have minus q times minus del u1 divided by the length, okay, plus 1. OK， 我们看到了，你的五个定律，能量法很简单，你通过微分就可以找到节点上的力，即便是 点力你自然会找到，但你分布力也可以用这个方法找。那分布力的概念是什么？它原本就是表面力，但分布力你要把它放到节点上，这个过程中，你的微分就帮你做了这个分配的工作。So in this case, we know very clearly the method should fit to the nodal force method. Okay? So you have the strain energy minus the work done by the nodal force. So this would work perfectly to match with the Castigliano theorem. But what's new about these energy methods is the system total energy method is you can add on the extra work done by surface force. And the displacement, because the surface is all along the length and the displacement is not uniform, in the case that when you try to interpolate the displacement along the length by a linear function, it is indeed possible to find out the contributions of the work done, okay, by the tip load. Okay. So that's what you have. Okay. So similarly, if you do the differentiations again, then you're going to find out how much is your distributed force. So this brings you the whole rationale behind why you have to go through that. Okay? Many times in your financial textbook they won't go through the rationale. So you'll be stumbled on why should I do this? Okay? The whole reason is there. It's just energy method, a technique to help you systematically resolve the force.
So is this in the book?
It's in the book, but you just need to rewrite them. They won't tell you why you have to do that.
What chapter?
No, it's in the book. Okay, in the also the lecture notes. Okay. But the book tell you this is a finite element procedure. They don't tell you why you have to do that. Okay. So but we prefer you understanding the rationale behind. Okay. So if you go through the lecture notes, it's doing the same thing, but you have to understand the rationale. Why do I need to, after Castigliano theorem, why do I need to consider minimum potential energy? So for these whole expressions, actually they are going to reduce to minimum energy that is at the equilibrium position. So the energy is going to be 0. Okay. So in this example, okay, we still consider the tip load. Okay, only toward the end, then I'll start about the surface force. Okay, the tip load is not just one spring tip load. It can be 2 spring tip load. When 2 spring is in series, you may have force on the right being the pull force on the left being the reaction. Okay, and the middle point might move by distance u2. The end point moved by distance u3. Okay? So how do you write the total potential energy? Very simple. You take the extension of the first spring, square it times K1 divided by half, divided by 2, then you got first contribution of the strain energy. And then next, take the strain energy contribution by the second spring. It's going to be half K2 times the extension of the second spring. Whether you write it U3 minus U2 or U2 minus U3 is the same because you're going to square it. But next, what about the work done by nodal force? Remember, in the expression for total potential energy, we are writing minus the positive work done. So what is the positive work done? When force is in the same direction as the displacement, it is positive. So minus P U3 is positive. It's minus positive work done. How about the work done by the reaction? the reaction is in the opposite direction to U1. So this is the negative work done. So minus negative work done give you the positive RU1. Okay? 所以你这个公式记得要念口诀。You must be able to read the meaning of formula. Then you don't need to memorize. If you can read it out, you get the convention right.
Reaction is F1.
No. F1, F2. It depends how you define. In finite element, you define everything along the x direction to be positive. Displacement also, everything along the x direction to be positive. But when you're doing your n calculations, sometimes you know reaction must be opposite to the pull force. Then you can define your own direction of the force. But ever since you define that, but the convention of the positive work done must be force in the same direction as displacement. In this case, this is opposite to the displacement, so this is negative work done. Okay, after you have these expressions, you take the total potential energy and do the differentiation. First differentiation with respect to U1, you got one expression. Next, you take the differentiation with respect to U2, you then get the force balance and not 2. And third, you do the differentiation with respect to U3, then you have the force balance and not 3. Okay? So when the theory is valid and lasts until today, that theory must reduce to what you learned before. Energy method, energy is something you don't touch, but it must be reduced to something you can measure. That is the force. Okay? So with this, then you can re-express the three equations, okay, into matrix form. Before we do this, what we have to do is let's put all the spring forces on the left hand side and all the external force on the right hand side. Okay? We do it on purpose, and the force convention should be follow the directional convention of displacement. If the force is along the displacement direction, it must be positive. If the force is opposite to the displacement direction, it must be negative. The only convention we stick to is the displacement or the coordinate you define. And then the force must follow that. Okay? After you have force convention determined, then you write the spring force on the other side. This is just moving the force from the left hand side to right hand side, nothing special. But the only thing you have to stick to is the force direction. Okay? Follow the coordinate convention. Then with this done, then you suddenly find that, hey, my energy method is doing me the sum of the forces automatically. Okay, if I do the partial differentiation. Okay? And this is what you call the auxiliary of the stiffness. But usually when we do the problem solving, we won't go through this step. But this is just to show you that if you are using the auxiliary of individual forces, summing up the individual forces and summing up the individual stiffness matrix, you're going to obtain something like that. Then this turned out to be something what we did last 2 weeks. Okay, you can identify which displacement is fixed, which displacement is free to move. Then you just take the matrix of stiffness associated with the free displacement and then subject it to external force, and then you do the solution. Okay, I will go through this, but please go back and do it yourself. Get familiarized with the matrix analysis. Okay, and I have to warn you, please do now. Okay, every time, almost every year, students got to repeat their quiz because a lot of your senior didn't master the matrix method. Because the example I use is still very simple. They keep using their Hooke's law, okay, to do new matrix method. Hooke's law for one element, okay. Two element, a little bit tricky. And I put it 3, then it becomes troublesome. Okay, so you better learn, okay, how to handle it. So for sure, I will give you 3 springs. Not one spring and 2 springs. That's too easy for you. That you don't have the need to use one element. Okay. So this is just a validation. Okay. After you do this matrix solution, okay, you can do this solution by simultaneous equation. You can also use the solution by the Cramer's rule, and you can also use the solution by the what we call Gaussian elimination. But to give you an idea how the solution is done, I think we better go through this simple example. Okay, the first thing I'm going to solve this 2 by 2 matrix, these 2 simultaneous equations, is by Cramer's rule, and then later I'm going to show you Gaussian rule. Okay, you have this solution. So you got to solve U2 and U3. Okay, the first thing we will teach you is how to solve this by Gaussian elimination. Okay, you might have learned how to solve the simultaneous equation. But I'm going to tell you Gaussian elimination. What's the whole purpose of solving? What's the procedure of solving this? Okay, the procedure of solving this is, if this is a stiffness matrix, I'm going to arrange them in C11, C12, and C22, 0, U2, U3. This is your, let's say, 1, 2.所以这个高斯相除法，我现在是直接告诉你最终结果。你就是要把它变成一个斜边上飞离。So what you have to do is make sure that it is non-zero above the diagonal, but 0 below the diagonal. So what is that important? If you manage to do it like this, you can start from the last row, C22, U3 is equal to P2. Then you can find from the last equation, U3 is equal to P2 divided by C22. Okay? Since you have solved this, what is your equation above? Your equation above is C11 U2 plus C12 U3 equal to P1. So your U2 is equal to P1 minus C12 U3 divided by because u3 has been solved in the last equation, then this can be written as P1 minus P2 times C12 divided by C22 divided by C11. So this is the essence of Gaussian annotation. Okay? This is just a procedure, it's an operation. Okay, but next, let's come back. How do we get to this diagonal form? To get to that diagonal form, you have to do some operation. Okay? Let's equation 1 here, 2 here. If I want to make this term to be 0, how do I do this? I might have the second equation minus the first equation divided by k1 plus k2 and minus k2. Is that right? Okay? So if you're really doing that, then what you're going to have? Your first equation minus k2 u2 plus k2 u3, and then the first equation is, after you do these operations, you have your this minus k2. Okay. No, I want to plus it so that it's going to be 0. Okay. So this is plus k2 divided by k1 over k2 u2. Okay. Times k1 plus k2. And this one is minus k2 times square divided by k1 plus k2 u3. Okay? In these operations, then the right hand side is p plus whatever you multiply. This is k2 divided by k1 plus k2 0. Okay? So this is then going to be cancelled out. The first term is going to cancel out. This is on purpose. Then what you're left is this term. Okay? You're going to have k2 times 1 plus k2 plus k1 k2 ku3 is equal to p. So in this way, you're going to find u3. Okay? So after you have done this, then you can, already move it. So your operations now is already solve this. Okay? But again, sometimes for 2 by 2 matrix, you need to do this operation. I think for 2 by 2, what you can learn about is your Cramer's rule. In the case of Cramer's rule, you just write your stiffness matrix first. Okay, this force, I purposely write them in the red color. Just in the solution of U2. I'm solving U2 because I just not solve U2 on the left hand side. It is a ratio of two determinants. The first determinant in the denominator is the stiffness method. The determinant of the stiffness method. Okay, and then because this is the second variable, the second variable should have the second column replaced by the right hand side. Okay, so this determinant is then k1 plus k2 times p. And then here you have the k1 plus k2 plus k2 squared minus k2 squared. Okay? So that is going to do the solution. Okay, cancel out. Okay. Yeah. So the expression in the end must be equal. So if something is wrong, then yeah, you have to double check. Cramer's rules and Gaussian eliminations should give you the same answer. So in the end, your U3 here is P over K2 plus P over K1. This is a summation of the contribution of individual spring extension. Okay? And now, next, we come back to the handling of the distributed force. We already tell you the displacement along the rod can be idealized as the linear interpolation. Okay? So now you can use x plus b. Just now your friend also tell you it's going to be u1 plus the difference u2 minus u1 divided by l and x. Okay? So next. So we have to realize that your finite element is just a spring. It handles n forces. You cannot handle any intermediate forces. So that kind of spring, you use Castellano, you use energy method. Okay. The same method can also apply to continuous rod. Okay. So a continuous rod, also called bar element, is straight. It is linear elastic, supported only by the axial holding. Axial force act on the bar ends. Okay. So this is bar element. Okay. Almost the same as your spring. Okay. It cannot handle intermediate forces. Okay. But how could we make it capable of handling the intermediate forces? Then we're going to express them next using these bar equations. Okay, if you have a bar being a small segment, okay, let's consider the stress acting on the bar. The left end is subject to stress sigma. The right end, which is away from left by distance x plus dx, okay, is subjected to the stress which is different from the left side. Let me draw the method. Okay, let's draw. This is a bar of full length L. But you cut it out somewhere here. It's away from the left by distance x. And then this one is the length. If you now look at this small segment of length dx, on the right hand side, okay, how do you define your tension? The tension here is, the stress here is sigma x. Okay, the right hand side is sigma x plus d sigma dx dx. Okay, so this is stress difference. And then next, how are you going to analyze the thing? Okay, you are going to find out these force balance. Okay. Because this whole thing is going to be balanced. Force dimension here is 0. How do you find this force? This is your area, which is identical on the left hand side and right hand side. If you multiply it with the stress, the force on the left hand side is sigma A. How about the force on the right hand side? It's sigma plus d sigma dx dx. Then your force on the right hand side is sigma plus d sigma dx dx times the area. If you now do the subtraction of the two, this is the force sum. If you do the subtractions, this is equal to fx plus dx minus fx. So in the end, what do you have? You only have the second term, d sigma x times dx a. So that's the force length. Okay, and then next, because force sum is 0, okay, force sum is 0. If you now bring the whole expression above, d sigma dx dxa, this is the force sum 0. So this thing is 0. The small segment dx cannot be 0. The cross-sectional area cannot be 0. So the only possibility is the stress chain along the length is 0. Okay? So, is it valid? Yeah. This is what you call your equation, governing equation. And then next, what are you going to do next? You're going to apply something you are familiar with. The stress is in proportionality to your strength. This proportionality E is your Young modulus. And then next, how do you find the strength? The strength is the chain of displacement versus the distance. Your strength is equal to du dx. You get it? This is your strength. Okay. So you don't need to memorize any formula. So you can draw a drawing. Okay. Then you have the formula. And then next, let's come to this. if you substitute these in here, you have your sigma equal to E dUx. Then if you do substitution over here again, then you have the E, and then second order derivative of this is equal to 0. Yeah. So that's what we did, right? Okay, ever since we have the governing equation now, later you can do the interpolation. We will go through with you. But let's graphically see how the distribution in U1 and U2 can be interpolated. I'll come back here. Alright. So here we start having interpolation, but now we're going to introduce you to the concept of shape functions. So means what's the inference of U1 to somewhere in between? Okay? So we're going to do these interpolations. This is nothing more than what your friend already tell you. How do I interpolate U here? Okay? I can straight away write Ux is equal to U1 plus U2 minus U1 divided by L minus 0 times X. Okay? This straight line. Okay, but I'm not happy with that. Why? Every time when I see one line, I have to look at the geometry and I have to write the equations. This is not what I'm happy, because it's very geometry dependent. But over here, what the mathematician trying to tell you is, I can rewrite these expressions by introducing you the concept of shape function. U at any point is called Ux. Okay? This any point is X. Okay? Ux is equal to the starting point plus the gradient divided by this displacement times length divided by length times x. Okay? But now I'm going to re-express these expressions into two groups. U1 group and U2 group. What is U1 group? U1 group is 1 minus x over L, and then U2 group is x over L. So do you see here? So now, this is the linear curve I have physically. But I can re-express them as what you call U1 shape function 1 and U2 shape function 2. So what's the feature of this shape function? For U1, at x equal to 0, it is 1. At x equal to L, it becomes 0. So this is your N1 shape function. And then next, U2 is multiplied with x over L. It becomes 1 when x is equal to L. So here you already can see my shape functions is something just a line of right angle triangle, starting with 1, ending with 0 next to you. So what does it mean? This shape function tell you how is your inference. what's the range of your influence? As I tell you before, force is transmitted from one node to another through the element. Just like you, if you're standing in a crowd, who can you push? You can push the guy in front of you, or you can pull by the guy behind you. What's the range of your influence? The range of your influence is as far as your arm length. Okay? So here is defining something. The influence is within the arm length of L. Okay? And that influence is decreasing as you go further away. Okay. So you can understand the shape function as the intensity of the force. How strong the push you can be. If somebody is closer to you and with your arm flexed, okay, that's the maximum force you can push. And you've already extended your leg. If you already extend your arm, how much force can you push in further? No. You are already pulled back by yourself. So the shape function will start with 1 at the local point and 0 at the next point. When we say point, we should refer to the nodes. 1 at the current node, this is N1. 0 at the next node. Likewise, for node 2, 1 at the node 2, position x equal to L. Okay? If you're not familiar with the right